Okay, so this is being recorded to the cloud, so anything you say will be recorded. Do keep in mind this microphone. This microphone can pretty much hear a flea fart in the next room, which is good because the sound comes through loud and clear. It's bad because if you're talking to your neighbor about something that maybe you don't want recorded on a class recording that gets shared with everyone, that will also get heard. And has also gotten heard before and had to be edited. All right. There we go. Got the virtual laser pointer going. I'm going to switch around the light because I think it's going to get washed out if I don't. All right, is that a little better for people in the room? Okay, so well, this slide's in from before. You're not the first cohort, but you are the second cohort. So the timings are still being worked out. The timing's actually not too bad. And the agenda is pretty much set now. So you're kind of like you're sort of like the one where I think I got everything locked down for the class, but just be advised they may shift some things around if I have to, but I don't think I'll have to. I'm assuming everybody did check out the course website and either has something like PyCharm installed, or maybe you already have like VS Code installed or something that you like to use. And you already found the source code for the class online as well. All right, so day one, introduction. I'm going to help anybody who's had trouble installing PyCharm. I know I got at least one of you during the earlier classes. I do encourage everybody to use an IDE, which is an integrated development environment. At some point, your code just starts getting you start getting a lot of code, and it helps to have a program that helps you keep it organized. It also, it turns out, helps you just code a lot faster, because it'll start detecting mistakes that you make on the fly. So if you made a typo in a variable name, it's going to actually tell you that, hey, you are talking about this variable, but it doesn't exist. You'll also just overall make less typos because a lot of these programs have autocomplete, particularly PyCharm. So it'll just know what variables you have available and what packages you have available, and it'll try and autocomplete. And so if something doesn't autocomplete, you usually know that you have an issue before you have something break when you try and run it. Yeah, so is there anybody who had trouble getting PyCharm up and running, or is having trouble figuring out how to use it or anything like that? Okay, let me know if you're in any trouble. All right, so I'm going to talk about what is version control, particularly what is Git. I'll talk about Git and source tree setup if you don't have it on there. I'll talk about how GitHub is not equal to Git, but Git is basically but GitHub is kind of a subset of Git, which is to say it's basically something that it runs Git, but Git is its own program. Is there anybody here who doesn't yet have a GitHub account? Okay, so if you don't have a GitHub account, now would be a good time to go on GitHub and set yourself up one. It's probably going to ask you to set up two-factor authentication, which is something you should get in the habit of doing anyway, now that everybody's getting their passwords compromised left and right. I'll also talk about what is containerization, give an intro to Docker, and help people set up and install Docker. So depending on how many technical issues there are, what I usually like to do on the first day is we're probably going to end early for most people. And that's because the first day, a lot of these things, just setting them up is honestly, for the first time, is kind of a pain in the butt. So I'm going to help you with getting your first setup going. Make sure you have kind of a clean installation, which means that once I finish up with the slides, basically once everybody has a clean installation, you're pretty much free to go. And then once I have everybody's installation sorted out, then class is over for the day. You will see me sort of jump around the room a lot during that time. So usually what will happen a lot of times, and don't feel hurt if I look at your problem and immediately sort of run away. Basically what I try and do first is just do a quick sort of triage, if you know what that means, other than the actual MD here who I know knows what triage means. But if you have a problem where I can get you out the door in with 5 minutes of basically tweaking stuff, then I'm probably going to get you out the door in 5 minutes of tweaking stuff first. If you have a problem where it's going to take me like 15 minutes to figure out why you have this weird thing happening on your computer that I've never seen before, then you're probably going to have to wait a little bit longer. All right, so anyway, so that's kind of the goal for today. Day 2 agenda, I'm going to talk about Python type hinting. So I think everybody in this room has already learned Python. Is there anybody here who has not done Python programming before? Okay, that's good, because I was going to say, much like the advanced class, if you haven't had any exposure to Python before and you're here, you're going to find yourself out of your depth fairly quickly. Has anybody used type hinting in Python before? No? Okay. But everybody here's programmed Python. So question for people, who's noticed here that Python is very flexible with kind of with variable defining? You know, especially somebody who's programmed in C, where you're like, this variable is an integer, it's 32 byte integer, and it's basically only that. Yeah, so C has very static, very enforced typing. Python has very dynamic typing, which is a variable is whatever you happen to store in that variable, and that's what that variable is. And if you switch it to another type accidentally, then you did that. And if you did it by accident, then you're probably going to get a lot of weird errors. Type hinting is basically Python. Python still does not enforce typing, although there are some packages coming out now that actually do enforce strict typing. But Python does not enforce typing. However, there is type hinting, which is basically your opportunity to say, especially when you're defining a function, that line that starts with def, you can actually say that this variable coming in is not just a variable that's coming in, but it's also expected to be of type integer, or it's expected to be a string. Or if you learn how to use the typing library, you can say this is expected to be specifically a list of integers or a list of floats. That can be very helpful for keeping your code organized. It's also extremely helpful when you hand your code off to somebody else at some point, so that they can see exactly what's expected to come into a function. It's also amazing if you have an IDE, because your IDE knows how to read that. And so if you're calling, for example, if you're iterating over a list of integers, you can actually call integer functions on the individual components of the list, and your IDE will autocomplete that for you. On the other hand, if you have the wrong type coming in, like you're passing in a list of strings when the function's expecting a list of integers, your IDE will start highlighting that and saying, hey, I think you made a whoopsie. So yeah, so anyway, we're going to set up a central repository for our work. So I'll be setting up the central repo on my account. We're going to review specs for our RPS project. Anybody know what RPS stands for already? Rock, paper, scissors. So we're going to review the specs for our rock, paper, scissors project, which we're going to be making a rock, paper, scissors game, and we're going to be extending it throughout the length of this class. So anybody here ever heard of rock, paper, scissors, lizard, Spock? Okay, get a few people. So we'll figure out how to extend it into rock, paper, scissors, lizard, Spock. Anybody here ever made a web server before? You made one? What'd you make it in?
It was in ShinyR.
Oh, okay.
In AWS.
Oh, nice. So that one's a little bit different, because that one's not like that. That one is an HTTP server, but that one behaves a little bit differently than most web server setup. Anybody here ever set up a web server in Python? You have?
Yeah.
What'd you use?
It wasn't Django, it was Flask.
You use Flask? Okay. So I'm going to show how to set up actually a very basic web server and run it inside your own computer. And that's actually another way that you can interface with programs. I'll also be showing you, what I'll be showing you how to set up is actually what's called a REST API. So it can send a web page, but it's actually much more geared towards exchanging data online. And if you set these up as web servers, you can actually make your tools available online if that's something you plan to do. I won't be showing you how to secure it, so you got to work that part out yourself before you make it publicly available. All right. Oh, yeah. And then, yeah, so we'll be building that project tomorrow. After we finish with the first part, we'll go over the results and we'll set up version 1.0, or we'll set version 1.0, and then we'll plan out version 2. For day 3, I'll be talking a little bit about how the internet works, which is getting us set up for building out the next step of our project, which is extend it out to rock, paper, scissors, lizard, Spock. And at the same time, also set it up to be a little web server so that we can actually play rock, paper, scissors in our browser. So yeah, we'll be making those updates tomorrow, and then we'll talk about other potential extensions we can do. This, by the way, is also the class that somebody suggested I make a class based on all the things that I wish somebody had taught me as a bioinformatician going into industry. This is what this is based on. These are like the two things that people tend to come out of academia not really knowing very well. And as soon as they get into industry, like people just expect them to know this, and usually they don't know it, and usually causes problems till they get it down. It's also the stuff where I look back over, stuff I was doing in bioinformatics in academia. I was like, I actually wish I had really known this back then, because it would have saved me a lot of trouble. So yeah, basically, quick introduction for this. Bioinformatics applications have become more complex and dependent on computing environments. Anybody ever encounter the problem of, hey, it worked on my computer, I don't know why it's not working on yours? Yeah, those are annoying. Anybody encountered the actually worse problem of, hey, it's giving me this result on my computer, why is it giving me a different result on your computer? Yeah, so bioinformatics kind of as a specialty right now has a reproducibility problem. There's sometimes some bioinformatics out there that has been published and it's out there. And I think actually a former collaboratory professor once actually wrote a paper basically saying that about half of the bioinformatic packages that are published are currently unusable because of like bad dependency management or undocumented dependencies or stuff going unavailable. So there's ways to address that. So number one, we need to be able to track changes to our bioinformatics packages over time. We obviously, if you're running on version 2 of a program, it's good to find out what changed between it and version 1. And if you're running on version 1.1, it's good to find out what they fixed from version 1.0, because maybe there was a bug and you want to rerun your analysis because there was like, okay, a bunch of these results are probably not correct. So we need to be able to track changes, replicate computing environments, and collaborate basically across computers, across sites, and even across the world. So yeah, about half bioinformatics packages are unusable. So let's see if we can start fixing the problem of, I don't get it, it worked on my computer. All right, so first off, why PyCharm? PyCharm is pretty much agreed to be one of the most feature-rich IDEs for Python. VS Code is a pretty close competitor. In fact, at some point one day I might switch over because VS Code is free, whereas PyCharm, if you're not academic, you have to pay for a subscription. VS Code is a Microsoft program. It tends to be very well supported. But PyCharm is also good. One of the reasons I bring up PyCharm specifically for this class, and although VS Code is actually coming very close to replicating it, PyCharm has the best Docker support of anything. Basically, there's just a setting or two you have to change in PyCharm, although I think that may have actually changed since I taught this class last time, but there's a few settings you have to change in PyCharm, and then it becomes like you're actually developing inside your container, where basically if something exists in your container, PyCharm sees it, and if it doesn't exist in your container, PyCharm won't tell you it does. So PyCharm has really good support for type hinting, auto-completion, all that good stuff. You can get a community or professional version, but if you're eligible for educational licensing, such as you have a UCLA email address, and I think also Cedars-Sinai email addresses work, you can get the professional edition for free. That gives you access to a lot more functionality like direct containerization and also much easier time building web servers. All right, version control systems, what's that? So this is a little bit more complicated than IDE. An IDE is just a program that helps you write code. A version control system is designed to help you track files over time, but it turns out tracking file changes over time in source code is actually not as easy as you would think. So version control system is likely to have the following features. You're probably going to have the ability to revert to a previous state, which is good because if you write a program and then you suddenly figure out that, hey, this new feature I built just slowed everything down and made it horrible, or worse yet, this new feature I put in actually broke a bunch of stuff, You can, in theory, just roll back to a previous version. I do typically tell people don't roll back if you can avoid it. Rolling back tends to cause annoyances. And how annoying rolling back is directly proportional to how far you're rolling back. So if you just set out a new version and you decide you don't like it and you want to roll back, that's usually not too terrible. If on the other hand you decide there's like some deep bug that got in there and it's from 3 months ago and like 15 versions ago and you want to roll back 15 versions, your annoyance level is going to go way up. So a lot of times in those cases, it's much better to just analyze what the changes were and figure out what's causing the problem, fix it, and roll forward. I know some people who just as a rule, they say they never ever roll back, they always roll forward. I don't subscribe to that, but I do say only roll back short distances. If you want to roll back a long way, prepare for annoyance, probably roll forward. So yeah, you can revert changes in a file, you can revert changes in the entire project. You can also identify the source of a change. So if you want to figure out who made a change or what change was made that caused a problem, typically that's going to be tracked by a version control system. It also generally should give you an ability every time you are committing or every time you're basically sort of officially like stamping off a set of changes as kind of a group. You should be able to kind of state the nature and reason for these changes. So sometimes it's as simple as fix typo in this file. Sometimes it's added this entire feature. And a lot of times, in fact, adding an entire feature, you'll have multiple groups of changes going in there, and that's usually called a merge. I'll talk about that in a bit. It may have also some additional features of allowing for collaboration between individuals and maintaining a central server for the project files. By the way, the central server for project files, that's actually what GitHub is. It's basically a fancy Git server. So different types of VCS you might encounter. There's local, and local can be as simple as just moving to a new directory, creating new files, and increasing version numbers. And this is the way a lot of people actually start off their version control, is just they have a version of the program that works, they title the directory something, and then they just basically copy paste it to a new folder and start making changes there so they don't break anything. It's a pretty simple system, but you know, it has its issues. So number one, it's prone to errors, it's prone to data loss. If you forget to actually copy the directory, or if you forget which directory you're working in, you're going to find yourself maybe changing the directory you didn't want to change. Also, obviously, the issue with local is if your computer gets run over by a truck, you may lose data. So some of the more programmatic versions, they may use diff or something similar to that to track differences, which basically is a program that just looks at files and says what changed between these two files. Local version control, bad idea for collaboration. So if you're not the only person working on the program, you're going to have a ton of problems where somebody's working on their part of the program, you're working on your part of the program, and now you have to reconcile those two things. That gets ugly really fast. And that's why one of the big advances was version control systems that allow for collaboration. And in general, local version control is considered pretty much out of line with most modern practices. If for no other reason than this one right here, basically everything is being designed nowadays so that if your computer gets run over by a truck, it's a disruption, it's not a catastrophe. All right, types of version control system going on to centralized. So centralized, it's always going to be hosted on a remote server. The official version of the files is going to be on some server that's probably got a regular backup plan. Maybe it's even in like some hardened data warehouse to prevent it from, you know, power outages and all that fun stuff. Obviously, it's only as secure as a central server. So if you don't have it on a good, strong central server, then if that central server fails, you still have data loss. For centralized, the user is going to check out a file, they're going to do their modifications, they're going to put the file back in. And to avoid conflicts, so this is what we call conflict avoiding. A a user who is editing a file will check out that file while they're editing it. And no other user can check out that file. So it's basically just who has the file for editing. This can be a problem if somebody, and this has been a problem in the past, when somebody checks out a file on Friday before vacation, and then they go on vacation and forget to check the file back in. That basically means nobody can touch that file for a week or however long they're gone, unless somebody actually just knows how to basically release the file from them. All right, but this is better for collaborating within a team because now you have some mechanism of conflict, at least avoidance. CVS and SVN are examples of this. You won't see these anymore because the newest and greatest is distributed, which solves a lot of these problems that even the centralized has. So with this one, everybody has a complete copy of the code at all times, or at least they have a complete copy of the current stuff. A lot of times if somebody's dealing with a big repository, they might leave off really old branches and really old versions because nobody's messing with those. So everybody has a complete copy of the code at all times. It's resilient against data loss. This is actually kind of awesome because when you think about it, even if the central server gets hit by a giant space rock, unless that giant space rock also hits everybody else's computers at the same time, in which case you probably have bigger problems, you can always just recover a copy from somebody's computer, or at least recover the most recent stuff from somebody's computer. This allows widespread collaboration. So, for example, I've collaborated on software with people in Japan, and we don't have to worry about the fact that I could check out a file and then decide I'm tired and go to bed, but I have that file checked out while the people in Japan are awake. That stops being a problem. The remote server generally handles the centralized version, but you can do local only development. So you can actually just run a local Git server on your computer and that's fine. Yeah, individual copies of files are tracked for where they are relative to the centralized system, which basically means that you can actually say, okay, the version on your computer is 3 commits ahead of the centralized version, or the centralized version is 3 commits ahead of yours, in which case update your version because you're going to run into trouble. You do checkpoints on your changes again by a commit. You resolve conflicts by merging. So that's basically where you're saying this thing that I've been working on over here, I want it to actually go into the main repository, or on GitHub, you'll say, I want to make a request to add this to the main repository. And then whoever manages the main repository will say, okay, your code is good enough and it doesn't cause problems, I'm going to allow it. Or they'll kick it back to you and say you need to fix something. And an example of this would be Git. There's also things like Mercurial. All right, so why Git in particular? Number one, it was invented by the creator of Linux to handle kind of the large worldwide development of the Linux kernel and parts of Linux. It's focused on individual snapshots of file state that are called commits. You'll do most of your work locally. So you do most of your work locally, you'll do commits whenever you kind of hit a checkpoint. So it's like, okay, I got this thing working, I'm going to commit it. And then from there, you can also do a push, which is I want to send it up to the central server. You're going to do most of your work locally again. So files will exist in one of 4 states, which is unmodified, so no changes versus original. Modified, which means it has changed versus the original. Staged, which means that next time you do a commit, the changes in that file are going to be added to kind of the official checkpoint. And then committed, which means you have actually made those changes, and now that version of the file is in an unmodified state because you committed the changes. And the big one is support for nonlinear development or branching. And this is actually really cool because what can happen is you make version 1.0 of your program, version 1.0 is working. You want to make version 1.1. You can branch off of version 1.0 so that you still have the main branch there. And the main branch is what people would use for their production work. And meanwhile, you can be working on version 1.1 without having to touch any code in the main branch. And the nice thing is because you have branching, you also have a mechanism for saying, okay, this branch is cool and it fixes the problems of version 1.0. It's 5 times faster, and it fixes this little bug we had where there was a typo. And you can actually say, okay, version 1.1 branch looks awesome. I'm going to actually pull this in. So now version 1.1 branch becomes main. And because Git records versions, somebody can still actually pull down version 1.0's commit But at the same time, somebody who just wants to pull down a copy of your program gets version 1.1 as the main thing. So kind of a cool setup. And the nice thing is everything here, all these changes, they're all tracked. You can actually go back and down to the letter see anything that changed. Okay, and then I'll do this slide, and then I think I'm going to call for a 10-minute break for 10-minute bio break. For people who don't already know it, the restrooms, women's restroom is behind the elevators over there. Men's restroom is up one floor, down one floor, also behind the elevators, because this building was built in, I think, the 60s when somebody actually said, oh, we don't need women's restrooms in a science building except on the first floor. So good news for everybody, it's not the 60s anymore. Except maybe in Florida. So as far as the how with Git, Git actually just has a couple of fundamental operations. You'll see a lot of fancier stuff out there, like, merge, force, squash, or whatever. But you'll notice first off, that's some variant of merge. Secondly, the force and squash are just sort of other fancy stuff. You'll also see people talk about rebase. We'll not worry too much about that because that's one of the not so core operations, but you'll see it come up occasionally. So git clone, that's going to be the first one you'll typically do. You're going to pull down a copy of the central repository to your system, and you're going to start tracking it locally. So that's basically saying, okay, I'm going to track this software locally on my system now, and I'm going to start messing with it. Branch, this is optional, but it's a good idea to do before you make modifications. That's just saying, okay, I clone the original repository because I want to put in some new feature or fix some bug I found. Typically, what you want to do is branch off of that and then say, bug fix for maybe some issue that's known. And that's what branching is for. You'll make your changes on there, which might even be just fixing a single line of code. And then once you figure out it works and it's fixed the problem, then you can so once you've created the branch, you'll do the modify. Once you figured out you fixed the problem, you'll probably do a commit. You might also then, depending on how long it's been, do a fetch or a pull. And that's basically pulling down the central repo again to make sure that everything on the central repo matches with what you have. And also making sure that there haven't been any conflicting changes to the central repo that might affect what you put in there. So maybe you fix the problem, but somebody else fixed the problem before you did, and now you pull down the new version and you have a conflict because your fix and somebody else's fix are competing with each other. So maybe you decide, okay, well, I guess I'm not going to fix this now because somebody else already did and it's already been approved. When you do a push, that's sending your branch and whatever else is associated with it to the central repo. So that's actually making your branch part of the central repository, but not part of the main branch or the trunk branch. So you'll see a few different names for the main branch. Sometimes it'll be called trunk, sometimes it'll be called main. Because of the sort of connotation of the word, people stopped using the word master, but especially for older repositories, you'll see the main branch actually called master a lot of times. But all those, if you see a name like that, it'll typically represent the main branch that's supposed to be the official one to use in production. So the last thing that'll happen is a merge. And the merge is what happens when you basically say that you are adding the, you're taking that branch and you're actually pulling it back into the main code because you like the changes. All right, and it's 9:50 exactly, so we'll pick up back again at 10 o'clock. And in the meantime, everybody's free, like I said, go use restrooms, go get water, stretch, whatever else you need. I'll stick around here and answer any questions you might have. I'm just going to get a drink of water first. Yeah.
I didn't see this was good on the. Class, there's nothing there. Is there class materials? No?
Oh, the source code for the class. We'll actually get to that in a minute, because for this class, the source code actually needs to come from the class GitHub repo, which we're going to put together.
A long time ago, I did do this like EDG workshop for the med students. That's at 11. I think we're gonna be done by 11.
Did you get did you get stuff set up on your computer already?
Have GitHub set up and PyCharm.
Okay, so you need help setting up Docker.
Okay, I'll do Docker.
Okay, yeah, download a copy of Docker.
Okay,
Since you have to go teach people how to read an EKG, I will get to you first.
okay. I won't, I mean, I'll leave it like, is that Geffen Hall, which I think I should switch parking lots.
Okay, like I said, I'll try and get you out of here. I'll try and get you out of here quickly enough.
Yeah, maybe like temporary.
Yep. Yeah, I got concerned a few years ago when I was living over in Weyburn, the student housing. I was actually like, I was the first year that they opened it. Well, at least the first year they opened Sycamore. I think the other ones had been open already. Sycamore was like the last one they had opened in the initial cohort. So I was like the first person living in my unit in Sycamore. And yeah, I remember a med student lived across the hall from me who I have mixed feelings about that guy ever graduating med school.
But we had a couple of those at my med school.
I was doing a ton of mouse surgery at the time. And I remember he was over in my apartment and he asked if he could, and he like asked me why I had that weird looking roach clip.
Was it Kelly or something?
It was, I forget what the exact name of it is, but it's basically the needle holders with the integrated scissors.
Okay.
Because I was like, those are really handy if you're doing a lot of mouse surgeries, which I was. You can buy the cheap Pakistani ones because actually like the best thing for suturing technique is actually practicing on an orange.
To be fair, as a med student, you don't get much hands-on surgery. They're not very nice to you in surgery when you're a med student. They kind of ignore you.
I know that, to be fair. On the other hand, if he had said, what is that? That would be much different than if he just assumed that, oh,
It's surgical.
that's for, yeah, that's much different than a med student not knowing what a surgical tool is. That's like one thing. A med student thinking that a surgical tool is for smoking weed, that's different.
That's what I wrote. I didn't get that.
Yeah,
I was thinking, nobody looks at us as surgery.
yeah, I know.
And you're not there, and then occasionally they're like close the skin. Or you get a really nice surgeon, but it's not that nice. That's why I'm not.
That's why they become doctors who work on people who can't be talked to or talk back.
Yeah.
Oh, and Julianne, to answer your question, yes, you should install those on your computer as soon as you can. But yeah, he had that one. He also had a bunch of other rather weird stuff going on. Like he came to me one time for help with medical genetics. And I had to go back and I had to go all the way back to DNA, RNA, protein.
Oh, wow. That's not good. I mean, the fact that you know that we use desfuroxine for anthracycline-based cardiomyopathy is insane. I didn't know so much medical info.
I read a lot.
Yeah, much. It's like I didn't learn that until I got to not just cardiology, but cardio-oncology clinic.
Well, it's also like a kind of an interesting chemistry issue there. Just like, oh, it turns out metal ion induced oxidation is like this thing that happens in a ton of places that nobody realizes it's happening, and it causes all kinds of issues.
Yeah. Yeah, no, I mean, you're right. I just learned that 7 years into my training.
Although to be fair, I never remember the name of the compound. I just remember that it functions as basically a specialized version of EDTA.
Yeah. Like a chelator.
Yeah.
I've never used it though. I think it's just like in the very acute setting.
I think part of that's because, I mean, oncology is moving away from doxorubicin type stuff because nobody wants to give that.
I know, but it's still like a lot of people still get it.
Yeah. I have a friend who was on it a few years ago. What? Yeah, he was on it for Hodgkin's, I think.
Yeah, I was just gonna say.
Not that I usually just go to the like stage explorer.
Okay, so I think we can pick up again. All right, so installing Git on your computer is going to depend on your OS. If you haven't installed it, best thing to do is honestly, and again, this comes back to the #1 answer for most bioinformatics questions that you don't know the answer to is just try and Google it, because most of the time you'll find an answer.
Is it Build Deck? Docker?
No, you should just be able to find it on Docker. Like it should be docker.com or something along those lines, or docker.io. Okay, yeah, I can walk you through in a few minutes as well.
I got it.
Okay. You will see a lot of whales because that's kind of their symbol.
I think that is what it is.
Okay. So yeah, installing Git on your system is going to depend on your OS. If you have Linux, you may well have Git already installed on there. Otherwise, it's very easy to install on most Linux distros. The one thing I won't support in this class, if you have some weird Linux distro, I might not be able to help you install Git, but if you have some weird Linux distro, you probably already have it on there and probably already know how to do it yourself anyway. So Git itself is a command line tool. Remembering all the commands is a pain in the butt. So I usually recommend getting source tree, which will run on Mac or Windows. I think there's also graphical clients for Linux. Although again, if you're using Linux, you're probably already more familiar with the command line. So I'm just going to go around really quick and see if everybody has it already set up and installed. So if you can show me Git, if you can show me a terminal where Git is basically a command you can run. So just if you type in Git, if you just type in Git and hit enter, it's going to typically say that you need to give it an actual command, but that's enough for me to see that it's installed on the computer. And then if you can show me source tree or whatever other graphical client you're using, PyCharm also has one built in. So if you don't have one on there, if you already are using one from PyCharm, like you would not find source tree on my computer because I just do all my Git actions through PyCharm. So I'm just going to come around really quick if you can have those things up, just so I get an idea of who's going to need help in a bit. Okay. Yeah, GitHub desktop, it looks like, because that looked like it was coming up. Yeah, GitHub desktop is also a valid one. A lot of people use that instead. That's like the official version.
Yeah, that's what I'm using.
Okay. Yeah. Okay. Yep. Yep. And then, okay, you don't have them pulled up, but you both have graphic clients on there?
Yeah.
Does it not? What? Oh, yep, you got first screen. Okay. Oh, you're on this computer. Already. What? So yeah, these computers are not going to have micro. Oh, okay. All right. Old school. Well, so the nice thing is you can actually do your development inside of Git using Emacs or inside of the Docker, because you can actually just go into the Docker and install and run Emacs in the Docker.
Yeah.
Yeah, you got it. And then you go first tree on there. You can install first. You're gonna have a desktop right there. Okay.
Well, I mean,
Yeah, you should do a search for either GitHub desktop or source tree. And install of those on your computer. It makes it a lot easier to do your workflow. I'm trying to get it well. Yeah, here you go. Here's the copy of the desktop. Okay, you have a working copy of the Okay, that was built in on Mac. Yeah, okay, I wasn't sure. I haven't used Mac for a few years, so I wasn't sure if they're still building anything, so they're still building. Okay, cool. So everybody has Git, and everybody has either gotten or is downloading a graphical client. Okay, so we can move on from here. People online, obviously, it's more of an issue to go over your screens. Let me know if you have any issues with getting Git on there. I'm actually going to kill my video feed just to save bandwidth. Oh, whoops, I lost my slide. There we go. All right, so GitHub. I think at this point everybody's heard of GitHub. I know when I first started teaching this class, GitHub was relatively new, but I think now everybody at least knows GitHub's where you go to at least get software. Fewer people know, fewer people know that GitHub is also a place where you just put your software there. Before there was GitHub, there was I don't remember the name of that site anymore. Anyway, before GitHub, there was what? Google had Google Code. I don't know if that's still up and running anymore, but nobody's using it. Oh, before that, there was SourceForge. SourceForge is still there. Nobody's using it, but SourceForge probably is making it. SourceForge kind of self-funds through advertisements, especially self-funds through advertisements that'll put malware on your computer.
Oh.
Yeah, if you go to SourceForge, there'll usually be like, there's like the little download button that will actually download the source code that you're after. And then there's like 3 big green download buttons that are actually parts of ads that will download something on your computer that is definitely not the source code you want. Like it will have Vladimir Putin himself reading your emails. So yeah, generally, if you have to go to SourceForge for something for some weird reason, be very careful what you click on. Or just see if there's some version of it on GitHub because it's probably newer. Basically, everybody's moved off SourceForge. So GitHub is not Git. Git is something that is, again, you know, it's open source software that was released by the guy who made the Linux kernel, Linus Torvalds. But Git is a version control system that exists as a command line tool. Yeah, so GitHub is just a centralized Git server that basically provides itself to basically everybody as a service. It's especially there available for people who are doing big open source projects. It also puts an HTTP interface in front of the Git server so that you can actually just view source code on your web browser. That's kind of one of the big changes it makes versus regular Git, which does not have that functionality. It also has some other things like better traceability. So along with the standard merge, there's also a pull request which actually lets you say things like, I want, you know, I made this branch, it's on a big collaborative project. I want the project administrators to add it. And you actually have all the records kept around just merging on a branch so they can say, we'll merge it, but you need to fix this, this, and this, and this part maybe needs to be brought up to our standards. So then you can actually trace that whole interaction back until when they say, okay, we think everything's good, we're going to merge. So yeah, this adds even more traceability than just regular old Git. And it's really designed for big open source projects where basically like you have an entire community working on the thing. So, all right, I'm going to go around the room again. If you can go onto GitHub and just show me that you're logged in. I just want to make sure everybody has their account set up. And then the other thing I'm going to have you do is sometime today, send me an email, or actually preferably sometime before the end of lunchtime, because I'm going to need to do this tonight. Send me an email with your GitHub username so that I can add you to the class repository, because we're actually going to have a repository for this class. So I'll set up the central one and everybody can basically start modifying on it and doing all kinds of stuff with it. Yes?
Could you put your email somewhere, like, so we can?
Oh yeah, sure. My email is not on the class site. Okay, I can actually just tell you my email right now. It's very easy to remember. michael.weinstein@ucla.edu. So it's literally just my first name dot my last name @ucla.edu, which is the cool thing about having been at UCLA forever is I got that email address before anybody else did. However, if you are on MedNet, don't try and email me at mweinstein@mednet. I don't actually still check that one regularly because I got locked out. I probably fix that while I'm here. Yeah, so that one I won't necessarily check.
Did you say there was source code somewhere that we should download?
There is source code for the class. You're going to actually get added onto the repository for it.
Okay.
So that's why I need you to email me with your GitHub username, because I can add you. I can add you from there. Okay, you're on GitHub and you have a login. You're on GitHub and you have a login. Do you have a GitHub account? Sweet. You have a GitHub account? Yes. Yep, that's a GitHub account. You have a GitHub account? Yeah, you're logged in. Okay. Okay. Oh, yeah, oh, leave it on that one.
Yeah, I'm working on it.
Oh, okay. Yep, that's you. Okay. That's all I need to see. Okay, cool. All right, so yeah, like I said, when you get a chance, send me an email with your GitHub username so that I can add you onto the class repository because I'm going to be making that later today. All right, Docker, and I do this one last because Docker is usually the one that is the most complicated to install. So, a couple questions that frequently come up. Who here has heard of virtual machines or VMs? Okay, a few people have. So one of the questions that frequently comes up by people who know virtual machines is a container a virtual machine? The answer to that is they're similar in a lot of ways, but they have some very, very fundamental differences. So virtual machines are much more isolated and they have much more strictly defined resources. Which is to say that if I spin up a virtual machine on this computer has 16 gigs of RAM and 4 cores on it. And if I spin up a virtual machine and I give it, and I say this virtual machine gets 2 cores and 8 gigs of RAM, then half my system resources are taken by that virtual machine. And the virtual machine can't increase what it uses. And the virtual machine will always use the virtual machine will always have those resources locked down, even if the virtual machine isn't using them. So on one hand, it can be very wasteful. On the other hand, it can be like very bad for scaling. So a VM just gets what it gets, and it holds those things even when it's not using them, and it can't go above, and it can't go above them. A container can be a lot more elastic. So a container will try and use as many cores as it's allowed to, if it's very active. But if it's not doing anything, it's typically going to release those resources back to your system. So containers tend to be a lot more elastic. Virtual machines tend to be a lot more sort of locked down on what they're using. You can almost think of it as a container has elastic sides and a virtual machine has very rigid sides. And basically a container is like running an entire operating system with built-in instructions of its own. So it's like running an entire operating system as its own computer program on your system. A virtual machine is really, as much as possible, trying to make it a separate machine within yours. So parts to Docker. First thing, there's images. And an image is a starting point for each container. So an example of an image might be Ubuntu 22.04. And that's a very common actually image to use. That's basically saying, I want to start with a clean Ubuntu. So Ubuntu does these long-term support versions, and you'll always see them as some even number .04. And that's because basically Ubuntu always comes out with a new long-term support version in April of every other year. So last year, for example, there was 22.04. And that was basically the long-term support version of Ubuntu. That means that basically that version they're going to keep updating and supporting for many years going ahead. Other versions in between don't get the same kind of long-term support. We're now actually closer to the next long-term support version, which should be 24.04. So in April of next year, there will be a new long-term support Ubuntu version. But right now we're roughly in between long-term support versions. But yeah, that's generally a good version to use. Another frequent one you'll see with Docker is Alpine. So Alpine is a very stripped down version of Linux. Nice thing about using Alpine is if you can actually get your package to work in Alpine, it means that you tend to have a very small container image to work with. So if you're building something extremely simple, Alpine is a really nice container to use because those build very quickly and you can save them and transport them around very easily. All right. A container. So containers when you put the image into action. Oh, I should also mention these images are layered. So if you'll start off with an Ubuntu container and then you'll keep building on top of it. So you'll say, I have this Ubuntu container. Or another really common one you'll see me use is Python. So like, I think for this class, I use a Python 3.10 container. And then you'll see that, okay, I'm going to install these Python packages in that container. So these Python packages are available. And then I'm going to copy my source code to the container. That's the layering approach. And the nice thing about the layering approach is you're building on top. So for example, every time you update your source code, if copying your source code to the container should be the last thing you do, because copying your source code is very simple. But it's also something you change a lot as you're developing. So typically you want to do your source code last, because what will happen is all the stuff that you did before that, it's going to reuse those images. So all the Python packages that were installed, it's not going to rebuild that image. It's just going to reuse that image every time. So that's the advantage of using this layered build system. The container is when you take one of these images that's defined and you put it into action. So typically you're going to be running some kind of application or service, or some kind of program. There's also the Docker engine, and the Docker engine is the thing that's sort of running all this stuff on your computer. It's also handling pulling down images and uploading images if you're doing that. And a registry is some kind of centralized server or a cloud-based system where you're storing images, updating images, and pulling down copies of images. It's actually a lot like a version control, but for Docker images. The nice thing about a Docker image is once it's built, it's built. So even if some dependency that it uses goes unavailable, as long as you have the image and you don't try and rebuild it, everything's going to still be fine. Some examples of Docker commands. So Docker used to just have Docker pull, but now they've decided they want to put image in front of it. And that's basically dividing what kind of command you're doing. So for example, Docker image, and then you're going to have your verb, which in this case is pull, and you'll have your noun, which is the version you want, which is a Python 3.11 container. Docker image ls, that's listing all your available images. Docker search Python, that'll search whatever container registry you're hooked into, which by default is going to be Docker Hub. That'll search it for the latest Python images, or for basically all the Python images. And then this command, which is a little bit longer, Docker image build. So this is actually building an image. -t, this is what you're titling it, or what you're tagging it. And then the dot is actually very important, even though people tend to miss it, but the command won't work without it. The dot is actually the context, and the context is a folder on your computer. And that's saying build it from this current folder. And in that folder, if you have a file called Docker file starting with a capital D, Docker will know to look for that file, and that's actually the instructions on how to build the image. So this will build a new container called my container using the current working directory as its build context. For container commands, so Docker container run, so this is actually going to put an image into action. It's going to run a new container built from the Python 3.11 image. This one, a little bit more complicated, Docker container run -d. So -d means that it's running as a daemon, or it's basically running in the background. -p, and this says open up a port in the container, so you can actually hook into this container through your web browser or through some kind of, you basically hook into this container through your computer's own internal network connection. -name, this is saying when I connect to it, or when I'm running this container, the username inside the container is going to be tester, and I'm running in Python 3.11. So very similar to this command, but it's now going to do a whole bunch of other stuff. It's opening the container, it's opening it in the background, it's opening up a network port for communication, and it's giving the container a name. Docker container stop, I think that's pretty self-explanatory. Docker container RM. So it's important to note that when you stop running a container, the container is not gone. You can actually restart the container. You can open up the container and look inside it. If you want to get rid of the container, you can do Docker container and then RM for remove, and then the name of the container, and that'll delete the container. You can also add RM to this, so you can just do --RM, and that'll say that as soon as the container is done running, just auto delete it. And I think that particular option is used more often than not. Yes.
How is it similar in difference with like content environments that image?
So have you ever tried, so you're on a Mac, it looks like?
Yeah.
Have you ever tried to run a Windows program on your Mac? Yeah, you can usually get like in some Linux programs you can get to work on there, like because the Mac OS is very similar to Linux. Could you set up a Conda environment that could run a Windows program on your Mac? Or are you still in Mac OS fundamentally in Conda?
Yeah, I'm still.
So if you go into your container, if you're in like a Windows Server container, for example, you can run full-on Windows programs in that. Like a Windows only program that fits within the capability of that container will run inside of a Windows container, even if it's on your Mac. Likewise, on this Windows system here, if I go ahead and run it, so BWA, the liner, will not run in Windows unless you go through all the trouble of setting up like the proper compiler and stuff. So BWA just generally will not run in Windows. And people who have asked me before how to get BWA working on a Windows computer, I always say install Docker, run BWA through a Docker container. Because even though you're on a Windows computer, if you're running inside of like an Ubuntu Docker, BWA will run perfectly fine in there, because as far as BWA is concerned, it's running in Ubuntu. I could not do that in a Conda environment. So yeah, it's definitely containers are much more close to virtual machines than they are to environments. It's also one of the reasons why I actually kind of stopped using Conda to a good extent, is you'll still notice certain things bleed through from your OS into Conda. Whereas if I'm running something in a container, I can be typically pretty certain that nothing from my host OS is bleeding through into Conda or into a container. You still get bleed through into Conda where you can find that like, oh, the Conda environment still doesn't work on somebody else's computer. It's like, oh, well, Conda wasn't actually managing that environmental dependency. Does that kind of make sense? Yeah. And you've probably noticed that too before, right? That there's stuff that gets into Conda from your operating system that like clearly would not translate over to somebody else's computer. All right, so a Docker file. And a Docker file is just a set of instructions for building an image. So it looks basically like native OS commands, except typically you'll have a command in front of them like run. The builds are duplicated, and there are definitely some good optimization strategies here. Like I said, because they're layered, you want the things to change least at the beginning and the things to change more towards the end. So, for example, here we have our base image, which is just Alpine latest. This command is in Alpine, telling Alpine to add pip, which is the Python package manager. Okay, yeah. So we'll install pipe. We're going to copy over the requirements file, which is a standard file for listing Python package requirements, and we'll copy that in. We're going to install the requirements. Here it's saying copy the application into the file, into the directory, copy the templates into the directory, telling it to expose a specific port. And then this is telling it when you run the Docker that you actually want to run this application. So this is kind of a very basic, this is a very basic type of Docker file. Okay, so I'm going to come back to this slide actually in 2 minutes, just because. All right, so I'm going to have everybody run a command in a few minutes, but first things first. So at this point, your system is going to be much more prepared for a lot more modern development with better tracking of your code, as well as better reproducibility of the computing environment. And tomorrow we'll actually start developing the app. For now, what I want everybody to do is go into your terminal and run this specific command. So it's docker container run hello-world. And what that's going to do is that's going to tell Docker, number one, you almost certainly don't have that container on your system, so it's going to pull down a copy of that container. When you run that container, it's just going to give you some information about Docker and tell you like what Docker can do. But the most important thing is this command won't work if you don't have a functioning copy of Docker. So I'm going to go around the room and just verify that everybody's gotten this up and running. And if I see the right output from it, then I'm just going to tell you you're free to go. And if I don't see the right output from it, then I'm going to see how we can get your Docker up and running. This is where I mentioned I'm probably going to be doing some triaging. So yeah, I'll go around the room right now and just have a look. Yep, you're good. Okay, I'll back to you. You get that computer working? You start up Docker. Okay. Hit command space. They can dock, yeah, Docker enter. Okay, so if you haven't run Docker yet, it's probably gonna ask you for the password because Docker actually does need some kernel level stuff, so it's gonna ask for basically your admin password. If you don't have an admin on your computer, you're gonna have trouble running Docker on there, so we'll talk about that if it comes up. And if you don't already have it running, start running the Docker desktop, which usually you just call up as an app on your computer. But now's a good time to call it up so that when I get to you, you'll already have it running. Because that command won't work if you don't have Docker desktop running. Yep, you're good. Yep. You're still installing. Go. What? Oh no, you pull, yeah, you're good. Okay. If you pull down Hello World and if you pull up the terminal, yes. So yeah, you see there where it says unable to find the world. Pulling the image from yeah, so it actually pulled that from online and it ran it. And that's the output. Oh no, it's not the image of the picture, it's the image. Yep.
Thank you.
All right, go to each of us, if people have it recognized.
We're not quite there yet, but that's gonna be almost.
Have you ever seen what it looks like if you actually look at the ion channel activity? It's crazy.
No.
It's like this weird psychedelic Indian pattern where it actually goes into full on EPIP.
Oh, wow. I mean, Torson is crazy on EPP. It's scary.
So usually you have most like walking through it, it's like they probably like I'm gonna dive into something about it.
What do you get?
That I don't remember.
Or like the classic boyard.
But I mean, oh, mag, yes.
And then probably have to shock the fence with walls, but.
Exactly.
Okay, it's kind of the same. Do something in front of us, get the. Feature, right?
Yeah.
Or,
We got like.
a bunch of.
Okay. Yeah, if you ever get a chance to see what it looks like in the like actual ion channel, it's like.
Usually they see them make them.
Like we did some, what's it made, one of those on the map in cardiology. Cardiology. Ask him if you ever see him, ask him to check out those images of because they're really crazy to actually what's happening with us.
Okay, cool. Bye.
You're good. Yep, you got everything ready. All right. Okay. Okay. Yep. Yep, you're good. Yep, see you tomorrow. You should have space on that thing.
I think so.
Okay, yeah, Docker doesn't take a ton of space, but it definitely likes to have hard drive space available. All right, so I think that has everybody sorted out, so I'm gonna actually end the share and end the show.